we have the least squares approximation down, we'll see how to use it to solve real life problems. So here's our goal. I'm given data, or I found data in the lab, and I want to figure out which curves fit it best, which model should I use for my data. So given data points x1, y1 up to xn, yn, which curve y equals f of x. I need to restrict myself to a specific type of curve. They might be polynomials of degree 3 or less. They might be, we'll talk about trigonometric polynomials later this. But we'll look at specific type of function. So which curve of a given type fits this data best. Alright, so let me give you an example. I'm in a physics lab. I want to find some sort of, maybe the Hooke's constant for a spring, something like that, and I measure a bunch of points using different weights and whatnot. So consider the points. Let's say I find at 1 I get 3, at 2 I get 5, at -2 I get 6, and at 3 I get 3. And let's say that I know that my data is supposed to follow one straight line. I need to figure out what the slope and what the y-intercept of that line should be so that it's closest to my data. So how can we find the curve that fits the line, that fits this data best? Alright, so in a case like this, let's graph them. 1, 2, 3, -1, -2, -2, 6. So 1, 2, 3, 4, 5, 6. I have this point. 2, 1, 2, 3, 4, 5. I have this one. 3, I got 3. And 1, I have 3. Alright, so those are my points. And I want to fit a line through it in the best possible way. Well, even looking at it, I mean, you could tell that some lines would be wrong, but do I want this one? Do I want it slightly higher since this one seems further? Do I want it slightly tilted like this, tilted? Do I want this one? I mean, I could come up with a bunch of different lines that would work. So I need an algebraic way of figuring out what slope I should take, what y-intercept, which would make the most sense in this case. Alright, so we're going to use least squares to solve a problem like this. Here's the idea. To apply least squares, you need a system. So we'll see. Well, the best case, the case that I would love, is if all my points were already on a line. Then I would just take that line for sure. All right, so that would be my starting system. So here's the idea. So if the given points are on the line y equals ax plus b, then, well, for each point I get an equation that must be true for a and b. So y1 would be a x1 plus b. Same for y2. Alright, so for each data point, I get an equation. If I can find a and b that fits all of this, if I can find a solution, a value for a and b that would work, that would be my slope and my intercept. Just a second, I think it might be, yeah, I'm sorry. This is what I would do in Cal, but in this context, they often put the constant first. So let me do it that way so it's consistent with your notes. Part of the reason we do it that way is we'll generalize it to higher power, and so we'll start with a and then b, c, d, and it'll be 1, x squared, and so on. All right, so really we're trying to consider this system. So y equals mx, where y is y1, sorry. I think I use v. Yeah. So y is actually the set of y values, which is why I'm going to use y as a vector. So those are going to be the constants in my system. Now my variables are a and b. So v, my variables, those are a and b. So a and b are my variables here. So since the xi, yi are my given points, they're actually numbers. So these are numbers, these are my variables, and then my coefficients. Well, the coefficients of A are always 1. So 1, 1, 1. The coefficients of B are given by the x, so I'll have x1, x2, xn. All right, so case number 1. Y equals mv has a solution v star, which is then y equals a plus bx contains all given data. So this would mean that coming out of your lab, every single measurement you made is bang on and fits that line model perfectly. Right? So this doesn't happen. So usually what we have is that there is no line that contains So there is no A and B value that would make all the points on the line, so we take the next best thing. Where we don't have a solution, we take the least square solution. So you take the closest thing you have to a solution, then you get this line, which doesn't contain all the points. It doesn't contain all the points, but it's the closest. So we'll call it the least squares line. Alright, so this is the next best thing to having a line pass through it. And you'll always get such a line, whatever your data is. However many points you use, whatever you want, you get this. And you'll also have the error vector and the error size. That's going to be good as well.